Okay, Faraday's law, and I don't care if you remember the name, just know what it means and when to use it. The way I've introduced it is simply, if you're changing the magnetic field in some region, then you can change the flux within any enclosed plane region within that larger region. And if you are changing the flux, then about the boundary of whatever that region is, you get an EMF, a voltage, that's equal to the negative derivative of your magnetic flux. So if the magnetic field is changing, you're getting magnetic flux, and if you look at the field in the right, or relative to the right loop, you can figure out quite a bit, and we'll see what that means. Okay. Now the introduction is simply, for a loop of wire, if you change the current in the loop, you're changing the magnetic field inside the loop. And if you change the magnetic field inside the loop, that creates an EMF that tends to fight whatever it is that's trying to change the current. So if you have a changing current, you have a changing magnetic field, you have a changing magnetic flux giving you an EMF in the direction opposite the tendency of whatever is driving the change. Okay, whatever voltage is driving the change in current. Typically, your flux is going to be proportional to the current. If you've got a loop, then the magnetic field that you create is proportional to the current, and the flux is proportional to the current. And the proportionality constant is what we call L inductance. And as you know, if you multiply the inductance by di dt, that gives you the EMF. Okay. Without going into tremendous detail on that, this whole idea then gets you into the whole realm of circuits and circuit devices. Now, with what we did in our last class, we did talk about a cylindrical capacitor. We have the idea of a capacitor. The voltage drop across a capacitor is Q over C, because, of course, capacitance is the charge per volt, okay, charge per unit of potential difference. And we have R Q prime is a voltage drop, because Q prime is just your current. Multiply that by your resistance, and you get your voltage. And that's, of course, Ohm's law. And now we have this that results from Faraday's law, if you wish. And this leads us to the equation for an LRC series circuit, where the EMF is the driving EMF. I used the word proportionality constant here and digressed for a minute to tell you that one of my frustrations with the preparation people come to multivariable calculus, a differential equation, even a calculus course, and a physics course, is the deficiency in the whole idea of proportionality and variation. Okay, this is something I started struggling with it personally in 8th grade. That's where we saw it. And people are getting things earlier now. I think my grandson saw it in 6th grade. But nobody ever understands it. Because, number one, it is one of the things that's a little bit abstract or difficult to understand for a lot of people. But when our top students come out and don't understand it, I have a problem with that. Fortunately, it's something you can remedy, and it's time that you did if you don't understand the whole theory of proportionality and variation. I could explain it to you in 15 minutes, but I'm going to let you look it up. It's really a middle school topic, but difficult for most people to master at that point. So I just kind of recommend that you look up proportionality and variation and just master the topic, because it helps you read and understand formulas. I don't preach formulas. I preach a couple of principles and everything follows from them. But you're going to be using formulas. Most people in this class are heading toward an engineering career, and you're going to be using lots of formulas, because there are lots of formulas in engineering that don't follow from first principles. There are formulas that follow from, okay, let's take this thing and study it and see what happens when we vary these parameters, and we don't know exactly why they vary the way they do, but this is how they vary. So it's a whole different approach than what you would use in physics. In physics, of course, we study simpler systems that we can really get a handle on and illustrate our principles and relate everything back to our theoretical principles. A lot of stuff in engineering that you've got, some sort of theory behind, but you don't know everything because your system is a lot messier than the ones we study in physics. And you end up with formulas, and there's a whole lot of proportion and variation in those formulas. You'll understand the phenomenon better. You'll understand the mathematics of it better if you have a good grasp of proportionality and variation.